Well, we've gotten a fair group of folks to jump on, so we'll get started. My name is Jean Swidler. I am the Executive Director of Genetic ALS and FTD and the Legacy. We are a group of people impacted by genetic ALS and FTD that have come together to focus on the needs and interests of our community. And one of those needs is to ensure that we have access to information that comes out about us. So we should be able to hear about it directly from the people doing that research. So in that spirit, we were so happy that Professor van Eijk took the time to do this event. And with that, I will kick it to you, Professor.
Thank you. Let me share my screen. Let's see. How does it look? It's okay?
Great.
Yeah. Well, thank you very much for introduction and also for the invitation. It's yeah, I really like it to be able to hopefully tell you something about like our findings, and it's quite a different message from what is out there already. So I think it's, yeah, I think these meetings are very important. So I have enough slides to, I think, to fill up the hour, but I'm also happy to have more like a, I don't know, like an ongoing discussion. So yeah, we can do like a formal presentation, but yeah, please interrupt if something is unclear or you want to have a discussion about something. Yeah, I think we have like the ability now to do that. So that's nice. So this work is conducted in our hospital. So I'm from the Netherlands in Europe. We have one of the larger ALS clinics here in Europe. So in the Netherlands, we're actually the only ALS clinic where most patients are being diagnosed, and then they go back to their respective more local hospitals where they receive the care. But in principle, we almost see all patients that are living with ALS in the Netherlands. So in one single center, so that makes us quite large. So we see about 300 to 400 new patients every year. And one of the studies that we're doing is about the C9orf repeat expansion and estimating the penetrance of it. So what we wanted to know is that, so if we see a patient and that patient has C9orf72 repeat expansion, and one of their family members has also carries that gene, what is the probability for that family member then to develop ALS? So that's really related to penetrance, and we did a study about that. So a little bit about like the introduction to the work. So I'm not totally, I wasn't totally sure how familiar everyone was already with C9 and ALS. But the exact cause of ALS is unknown. But what we think is that it's something like an interplay between your genes and your genetic mutations that you may or may not carry, and some kind of external environmental risk factors that you're being exposed to. And those two combined probably make why some patients do, or some people do develop ALS and others don't. And the reason for like this combination between genetic and environment is nicely highlighted in this study, for example. So what they did in this study, and it's already 10 years old, almost, where they looked at twins, and both of the twins were carrier of the C9orf repeat expansion, but not both of them developed in the end ALS. So there seemed to be like some kind of discordance. So that what it means probably is that having only the repeat expansion or having only the gene doesn't necessarily make that you will get ALS. So you need something else, maybe some external factor to really go beyond like a threshold. And if you surpass that threshold, then you will develop ALS symptoms. So it's also a bit related to like the 6-step theory that was introduced by the King's College researchers. So there are many genes available now. So over 40 genes are available, and I think the C9orf repeat expansion is one of the most famous ones. It's also the most common ones that we see among patients. So from all the patients that we diagnose in the Netherlands, about 7 to 8% of the patients is carrier of this gene. What is maybe logical is that patients who also have like an active family history, where ALS is coming, has been observed brothers or sisters, or maybe at uncles, or maybe the mothers or the fathers. We see that about 45% of those patients carry are carrier of the C9orf72 gene, and if patients do not have any familial history, then it's about 5% of all patients. So it's relatively common that we observe, and in our center, and I think in most of Europe, testing for this gene has become like the standard diagnostic workup. So basically every patient that's being diagnosed with ALS will also get like a full gene panel, and we will evaluate like the 30 or 40 genes that are available there. And then if we do find that the patient is a carrier, and in this case the carrier of the C9 gene, one of the first questions is always like, so now I know it's genetic, and what am I going to tell my children? So what is their risk now of ALS? And yes, unfortunately, the gene is inherited like with a 50% chance, approximately. So the children have a real risk of being a carrier. But what then the actual question, of course, is then if I'm a carrier, what is the probability that I will get ALS when I'm a carrier? So this is really what is going to be this talk about. So about this probability to get ALS when you're a carrier, and that's what we call the penetrance of a gene. Now, if we look in the literature, then you will and look for what is the penetrance of C9orf72. So this is basically what we want to know. Then you will end up with probably with this study. So it's published over 10 years ago now in the Lancet. And this graph, what we can see here is like on the x-axis is the age of the individual. And then on the y-axis is the risk of getting ALS. So you can see that if the individual is below the 20 or even below like the 30, you can see like that the risk of getting ALS, even if you are a carrier, is very low. And you can see that basically the most patients will develop then ALS when they're around 60 years old, and then eventually all patients will develop ALS when they're 80 years old. And what we learn from this curve is basically that it says, so if I'm a carrier and I live long enough, if I get 80, there's a 100% chance I will get ALS. So the penetrance is 100% basically. And this study has been replicated many times. So this was the initial report, but then there were, this was my quick PubMed search. Then there were at least 4 other studies that I could find very quickly that showed like similar curves. So they always show the same curve of like the age of an individual, and then like the cumulative incidence or like the risk of getting ALS. And you can see that always those curves are getting to 100 or nearly to 100. So it doesn't matter whether the patients are Australian or whether they come from another population. And you can see it also for other forms of ALS or maybe only FTD, that the penetrance of, as soon as you carry this gene, you will get ALS. But the problem here with these studies is, and you can see it already a little bit in the title here. So these are Australian ALS penetrance for C9orf positive ALS patients. So that means that what they're doing is they observe all C9orf patients that already got diagnosed with ALS, and subsequently they looked at when did they get ALS, and this is how that curve is then being created. And as you can imagine, because everyone in that population has ALS, because this is where you selected the patients from, that those curves will always go to 100%. And that might indicate that the penetrance of ALS is actually a little bit overestimated in these cases. So what you probably think then of the literature is so that as soon as you have C9orf72, you will get ALS. And this is what I would like to challenge with this presentation. So as I stated, the problem of most of these studies is that they have selected already made on the outcome. So you already knew that the patient was going to have ALS. So those studies don't really answer the question, what is my probability of getting ALS? But what they say is, what they answer, the research question that they answer is, if I already know to get ALS, and when will I get it? So it's actually a retrospective question. But in my opinion, a more relevant question is, if I carry the gene, what is my probability to get ALS? And then if I will get it, when will I get it? So it's a slightly different question, but I think it's a very important difference, because this question, in my opinion, is actually never relevant, because you want to inform someone who doesn't have ALS yet about what is the probability of getting ALS. You don't want to tell someone who has ALS when did he get it, that the patient can know himself also already. So that requires a different approach. And how can we answer that question best is by actually a follow-up study. So what we want is to know a whole big group of people who carry the C9orf genotype who don't have ALS yet. So imagine this is a whole group of people. So this is, for example, all patients that are being born with C9orf. And what we can then do is we simply follow up the whole cohort for, let's say, a couple of years. And then at the end of our follow-up time, we're going to determine who of that cohort got ALS. So in this case, there are like 2 people out of the so many people that we measured. So this seems very, very simplistic, and because then we can just count like what is the probability of ALS is simply divided by the number of people that we got. And that is actually our penetrance estimate then for the follow-up time that we use. And that sounds very simple, but the problem is that this is the challenge of getting such a database. So we need to define this group of people with C9orf that don't have ALS. So how do we get to that? And that's like where the challenge lays. So the only possibility that you have is that you do like a very large genetic study. Let's say that we have 10,000 people we're going to test for C9orf. And only, well, what is the prevalence of C9orf among healthy people? It's about like 1 in 1,000. So we only got like 10 people then who carry the C9orf72 gene. And those 10 people we then need to follow up for some time. And the 10 people is usually, I think, is too small. So we need to maybe genotype 100,000 people or maybe 1 million people to get enough sufficient sample size to really say something about what is the risk if you carry the gene, the risk of developing ALS. So that means also not only a very large study population that we need to genotype, but also like the follow-up duration needs to be sufficient. And ideally, if you want to say something about lifetime risk of getting ALS when you carry the gene, you would need to follow up those patients for 80 or maybe 100 years into the future. So these studies are infeasible. Especially if you then also think about like, oh yeah, and then for all those 100,000 people that I genotyped, I also need to do regular follow-up to make sure that I don't miss any ALS cases. So that's another complication. So that makes it very difficult to do such studies. But we wanted to approach that, and this is how we, in the end, consider that. So what we do know from initiatives like Project Mine, and I think in the US there are also a couple of initiatives for like genetic databases, excuse me, is that we can identify all patients with ALS who also are like the C9orf72 carrier. Then from those patients who do have ALS and do do have the gene, we can ask about like familial data. So how many patients or how many siblings does that patient have, and how many of those siblings got ALS or do not have ALS, or are they still alive, or did something else happen? So we can collect that data from the patients that we know. And then from the literature, we can learn something about like what is the probability of C9orf. So if I'm a C9orf carrier, what is the probability that my sister also has C9orf, or what was the probability that my parents also have been carrier of the gene? So we know from the literature that's about 50%, of course. So if we do that for one patient, so suppose we have one patient that I see in the clinic and that is being diagnosed with ALS, and I can test that patient, and I now see, okay, that patient is a C9orf carrier. What I can then ask the patient is, can you reconstruct like your first degree siblings and relatives in this setting? So in this case, the patient had two siblings, so a sister and a brother, and of course, a father and a mother. What we can then ask is what was the status at the time of that I'm asking the patient, what was the status of, or the vital status of that person? So the mother was already deceased, the father deceased as well, but he developed ALS. The brother and the sister are both alive, and I know a certain age. The problem here is that I, of course, don't know the genetic status of these first degree relatives. But what I can assume, of course, is that, well, if I assume like that this is not a de novo mutation, and we will talk about that later, that C9orf gene must have come from either the mother or the father. So there's a 50% chance from every individual, from every parent, that he or she was the carrier. And the same goes for the sister and the brother. So that the sister is a carrier of the C9orf gene is 50%, and for the brother as well. And you can imagine that this is only one index patient with C9orf. But if I have many index patients, you can see that you can create a whole population of first degree relatives. So I'm only going to look at these gray individuals, and the green one I disregard. Now, basically what I'm creating here is a whole population of first degree relatives of patients who I know are carrying the gene. So I know that in these families, there must be this C9orf gene somewhere going around. I know the age of these individuals, so when were they born? And I know at the time that I asked the patient, more information about that individual, namely, was that patient still alive at the time of the questionnaire? And if not, when did he or she die? Did that individual develop like ALS, or was the individual still alive? So I know something about the vital status and how many of those individuals developed ALS. And the interesting thing now is that we know more even than that we asked for in the questionnaire. So we can also say, well, we know that the gene is inherited in a dominant way, so that 50% of them, about 50%, must be carrier on average. So if we take like 1,000 people, first degree relatives, to patients who carry the C9orf gene, all of those relatives, about 500 of them, so 50%, should be carrier of that gene, just because of like the inheritance pattern of the gene. And what we can also assume, and this is what we want to estimate, so what I want to know now is that what is the probability of getting ALS if I'm carrier? So what we can say is that all of the ALS cases that we observe in the first degree relatives are due to the C9orf72 gene. So if we go back to our example, so here I observe this C9orf, this ALS case. So then I say, okay, then this individual must have had the C9orf case, the C9orf gene, and this one did not. So that's something that we can assume. Doesn't have to be true, of course. Could also have been that just by chance the mother was the carrier and the father was actually the non-carrier. But what we want to estimate is like that if you carry the gene, then automatically we will say, okay, then, and if you developed ALS, then those two are connected. So you get like an upper limit of that risk, because if I would have said that the gene belonged to the mother, but she didn't develop ALS, and then you will understand that the risk goes lower of being a carrier. So by doing this first assumption, so that all of the ALS cases are actually due to the C9orf in our population, I try to overestimate the penetrance. And the same goes for de novo mutations. So I assume that all of the ALS cases are indeed related to C9orf, and even if that happened to the parents, I'm gonna assume that was the same kind of genetic mutation as what was causing ALS at the patient level, and then again, that will give you an upper estimate of the penetrance. So, using these two or these three rules, then we can say something more about our population. So remember, here we have like a whole population of first-degree relatives. So these were all patients reported, but we can now assume that 50% of them was a carrier. So we can take away like half of the population. And we also assume that among all the ALS cases, so here given in red, those were attributed to the carriership. So we can also estimate. So we know like for how many carriers in the end developed ALS. I will not bore you with all the statistics that go behind it. But what you have to account for is the fact, so if black means that the patient or the individual, the first degree relative was diseased already at the survey, but didn't develop ALS, that patient is basically, that individual is encountering like a competing event. Because maybe if the individual didn't die, but lived longer, he could still have developed ALS in the future. And for this green individual, yeah, that individual is still alive at the time of the survey. So that individual is still at risk of developing ALS. So we need to account for that using a statistical model. So this is what we did. So here you can see like the three different groups. So we had, in the end, we had about 900 first degree relatives and they were all related somehow to the C9orf patients. And then, of course, we know like the ages, and then we can reconstruct actually the probability curve of getting ALS. So there's like this competing event. So some individuals may die, and they were still at risk of developing ALS, but we need to account for that. And here you can see that out of the 900 first degree relatives, about 82% got ALS in the end at the time of the survey. And if you calculate that, and because we assume like that only 50% of these were carrying of the C9orf genotype, yeah, you can, and you account for like the missingness and the censoring, you can in the end estimate like the actual curve. Oh, sorry. Which comes up to like about 25%. And this is a very much different number from like the 100% that we estimate, because now we didn't select at all at individuals not having or having ALS already. So we didn't select on patients having ALS and then look retrospectively when did they got it. Now these are all individuals in theory that were at risk at developing ALS because they were carrier, and then what is the probability of getting it? And that gives a very different number as compared to what has been reported. Now there were, of course, a few assumptions that we made. So we said something about like carriership, but it could be that, for example, in our first degree relatives, not 50% is carrier of the C9orf genotype, but it's about 40%, because maybe there's some kind of embryo selection going on, or maybe people die earlier somehow. They have maybe a riskier lifestyle. Who knows? So it could be 40%, but could also be working the other way around. Could also have been 60% carrier. So these are like, we can update those numbers then and then rerun the analysis, and then you can get like different estimates of your risk estimate. So here you can see like the average, which was about 24% at when you're 80. So you have 24% risk of getting ALS when you're 80, and you carry the gene. And then you can see if you change those assumptions, how that risk is differing. So it's but like the uncertainty in that risk estimate is still within that confidence interval. And we did all kinds of sensitivity analysis to see, to check whether something really made a difference. The one that's interesting is here at the parents only. So remember that we have, basically these kind of data. So we have from the parents and we have from the siblings. So we can also repeat the analysis only with the parents of patients. So how many % of the parents in the end developed ALS or died of a competing cause? So we can replicate that analysis. And then you see you get much lower penetrance. And this is probably because of some underreporting or like underdiagnosis of ALS, because those parents, well, the average patient that we see is about 65 years old, so their parents must have been diseased already for quite some time. So the time that they developed ALS must have been maybe in the 70s, 80s, somewhere there. And then there was, of course, much less knowledge about and awareness, I think, about ALS, at least in the Netherlands there was. So that this could be due to some kind of underdiagnosis. And you can see that if we only select the siblings, then we also get a higher estimate. So then it's about 31%. So what is the actual truth? It probably is still somewhere in the middle. But it's an important finding that we had. Now, another important finding is that on average, we found like that the risk of getting ALS was about 25%. But that's really dependent on the familial data that we used. So this is a quite difficult graph. So it's like a relative risk estimate. So on average, patients have like they have like a relative risk of 1, so which means they just have like the expected penetrance, so which was about 25% at when the individual is 80. But we also observed like families that had lower penetrance risk, so much lower probability. So and we expect this as a relative risk, so about like, I don't know, 25% lower than what's normal. But we also had a few families that had a very much higher penetrance risk. So and that translates then about to like a 60% penetrance in some families, while in other families it was only 15%. And here's just an example. So in this family consisted out of 11 first-degree relatives. So none of the parents was affected by ALS in the end, and more than half of the siblings got ALS. So if we assume like 50% inheritance, so basically all siblings that got like probably that got C9 also got ALS. But yeah, this is only one family. So what happens in those models is that it shrinks a bit towards like a common way. And this is also something that we observe in other studies.
Ruben, maybe this might be a time to just jump in for a little conversation. Is that okay?
Yeah, sure, of course.
Jennifer has a question in the chat that I'll read out since I know you can't see the questions.
Yeah.
Could you predict the higher risk families?
Yes, so that's something that we're gonna work on now. Is that if we know like the survey data, so if we ask identify a patient with C9orf and then we send them out the survey and we got the data back about their family history, so we try to develop now like a model where that's already incorporated, so that we can indeed make better distinction between which is a high risk family and which is a low risk family. But that still requires input from a patient. So at one point we would like to go to more like that you have like the whole pedigree like even further away. So now we only ask about like first degree relatives, but also that you go to, I don't know, second and third and fourth degree relatives. But that's indeed what we try to develop now as a consequence of these results, so that we really want to distinguish who are the high risk families.
Wonderful. Thank you so much for that. And I know that you've been very clear that it's a probability of ALS, but for our listeners, you know, your survey did not ask about dementia or FTD or anything like that. So that is a little bit of a missing thing there, and I know you'll get to that later. I do have one other just question about this slide. These people with the very low risk, you know, it seems to me like there could be a chance that those people are how many of those are just one person in a pedigree? Because if they're the people with just one person in a pedigree would be more likely to, if there were any de novo, they would probably be the ones more likely to have a de novo. So just curious about that at all.
Yeah, no, so that this is independent of like family size. So we see like this in the paper. There's another difficult figure. I left it out here from the presentation, but what we show there is, so you can if there was like a constant penetrance, like the penetrance was like the same for every family, then you can estimate like how much variability would you observe if the family only consists out of one individual, out of two, out of three, or out of four. So you can give like some kind of confidence line around it. And what we see is that among all family sizes, there's more variability in like these probabilities among individual families than that there should be if there was like only one penetrance estimate. So that really gives us confidence to say that there's not one single penetrance estimate that we can give to a patient. So on average it's 25%, but it really depends on like the family history. So for some families it will be 25% is much too high, and for some it's much too low. So we need to go to like a more family specific estimate. But yeah, these lower, and maybe that's if I go to the next slide, maybe here's like the nice example. So this was one of the lower, so family A here is a low risk family, which is large number of individuals, and this is like a bigger pedigree, where this was the index patient. So this one was the one that received the survey, and then he or she provided all the data about the other family members. And here you can see it was like really only this patient that developed ALS, and there was many other individuals that never developed ALS. So that's like relative risk of about 60%. So there's a low risk. And then on the other hand, we have then this high risk family where there was one index patient, and I think this is the one that I showed on the previous slide. Yeah. So the 5 out of the 9 other brothers and sisters also developed ALS. So there's really a big difference, and there's many other pedigree examples from this. So there's really a continuum somehow. Yeah, so I think it's one of the last slides. I think the main message what I would like to bring to be aware of, at least, is that like the studies that have been out there, most of them have selected on having ALS and then looked at when did the patient get ALS, but that doesn't give you the probability of ALS. It just tells you when do you get ALS if you already have ALS. So what you really want to estimate is that from people who do carry the mutation but don't have ALS yet, what is their risk of developing ALS in the future? And this is something that requires a different approach, and this is what we try to approach here. Of course, some assumptions had to be made, but the probability that we found was then indeed lower than what long has been assumed. And this has some important consequences, I think, also from like the information that we give to patients. So we cannot simply say that if you're a carrier, then all of your siblings are also gonna develop ALS, and if they're also a carrier. But also has consequence, of course, for drug development, especially with like studies going on, like the Atlas study, where we try to prevent ALS from developing. So if we find like a patient at risk, so that would normally be like a carrier, and we're going to try to treat them and we try to prevent like symptoms from happening. We need quite a different sample size that if we know all of those are going to develop ALS versus only 25% of those are going to develop ALS. So that makes it says some consequences there as well. But another important conclusion, I think, is like the likelihood and the large differences between families. And yeah, this really is quite interesting. So it means that like not every C9orf mutation, maybe it's like a different mutation, maybe there's like some epigenetic factors that's influencing why some families have a more penetrant form than others. And like what you said, Jean, is that we indeed don't have FTD estimates, because that's like another. So if you carry C9orf, then there's increased risk also of developing FTD. That's something that we could not capture in the questionnaire. It was difficult because it's difficult for a patient to ask if it was really FTD or was it maybe like some form of an Alzheimer's or Parkinson's, and yeah, it becomes quite technical. And ALS is quite usually the patient knows what their siblings or parents had, but for when it comes to dementia, it's there are so many different forms of dementia that it's hard sometimes to learn which one was actually FTD and which one was another form of dementia.
Just a point on that. I think it's like accepted in the field right now that the presence of the C9 mutation in autopsy means it's not a Alzheimer's case or a late case. Like there's guidelines for performing autopsy for patients with TDP-43, and they say test for DPRs. If they have DPRs, then they're something else. So it's an interesting, I know it's not settled, but just thought that would be an interesting point to raise. But there's a lot of questions in the chat, but I'm sorry, I continue.
No, that's my last slide. So I have the final slide was about the paper that we wrote. So if there's a little bit more information there. But yeah, let's. I'm happy to take any questions about
it. Thank you so much, Professor, for this wonderful talk and for your team working on this over many years. How many families did not have cases in prior generations? Do you have that broken down, or?
No, I wouldn't know that out of the top of my head, but there were quite some. There were some families where there was like no ALS, at like higher generations, but it's. So here we really looked at the first degree relatives. So we didn't really look at like second degree relatives or aunts. So I'm not sure if I can give like an accurate answer to that. How many exactly there were.
No, very reasonable. What would this distribution look like if the true rate were 25% for all families? And how do you account for variability when estimating family-specific penetrance?
Yeah. So if the distribution was like. So in the paper, there's like a figure. I think this is panel A in the paper, and then there's another panel B from the same figure, and there we give like a gray shaded area, and that is like the distribution. This is how it would look like for like the size of the family, what the variability is, what would be within normal ranges, and I overlaid there like the variability that we observe, and you can see like the large increase. But if we would give it here, so probably like these, like probably it goes like somewhere between 1.25 and something point I don't know 80 or something. So much more narrow is the variability. If it would just be like a chance. But the true penetrance is 25%. But we observe like it's much more variability than what we would expect if it was a single penetrance estimate.
One of our attendees looked at the table in footnote 1 and said that the index cases may have had ALS and or FTD. Is that true, or are they only ALS? Because I thought they were only ALS, but
no, they could have had ALS and FTD.
what about, would they have had standalone FTD or?
No.
Yeah.
No, that's really ALS, but it could be like about like 5 or 10% or something have FTD like symptoms with it, but those are also included, but not alone FTD, not no.
So Kenny, just so you know, you just heard him say in their ALS cases, he maybe 5 to 10% would have full-blown FTD along with it.
Yeah,
that was another question. So
yeah.
Ronan, would you like to go with your question?
Yeah, thank you. Professor, thank you very much. It's very nice, very clear work. I was wondering, I imagine there's some subset of the family members who have been tested. So is there a way to do a bit of a validation study on these assumptions, given, where you know this?
So we did that. I'm not sure if those numbers ended up in the final paper anymore, but we do have indeed from like the 900 relatives we had, I don't know, like 20% or something, we had actual data of those. And there we see it was like carriership was about like 54-55% about, so yeah, we could validate some of the assumptions.
No, that's great. The other question,
Oh, go ahead, Ronan, sorry.
The other question I had was around anticipation, whether you saw earlier onset in second generation compared to the original parents where case age was known.
No, that's not something specifically we looked at, but I looked at these relative family risks, if those were related to age of onset, and those showed like a trend. So the higher the family risk, usually the younger the age of onset also was from the index patient in that case. But that somehow makes sense also. Yeah.
Okay, thank you.
Ronan, just a point on that, and Professor, maybe this is something also to consider, is there are these longitudinal studies of C9 carriers that haven't been around for very long. And while the overall number of converted cases in these studies have been relatively small numbers, they actually, like for instance, Dials has had like 6 ALS or C9 converters over like 3 years out of 100 people. And for a disease with a variable age of onset of decades, to have that many converters in just in that pool of people in a short time would not indicate a low penetrance. So there are these interesting things that complicate it a bit, and maybe those are more, people might volunteer for research more if they're in the higher impacted families. I know that worked for me. I
think that's a very interesting point. So I'm not saying that this is like the real definite estimate, because it's not the ideal setting, of course. So the best is like the study that you described, that you indeed observe these individuals, and maybe in those studies it would be very interesting to see, can we replicate a little bit of this curve, because but I can understand that even so if all of those individuals are around their 65 years old in that study, and there's 100 of them, that's like also the highest rate where you would expect like this transformation from like healthy to sick. I'm very curious. So if they would be very interesting to make like these kind of curves for that ongoing study, see how that looks like.
Totally. And I did not get a full question from our resident biostatistician, Daniel. So I wanted to make sure that his full question got out, which was also, how do you account for variability when estimating family-specific penetrance rate? And Daniel, of course, feel free to jump in if I translated that wrong or it needs further clarification.
Yeah, so the question is, how do you estimate variability if?
When estimating family-specific penetrance rates.
Yeah, so yeah, that's more like a.
Let me, if I could just
elaborate.
Could you go back to the graph that has the distribution?
This one.
Yeah, so, if you have 60% observed in a family, or 40%, presumably your estimate wouldn't be that. There would be some regression to the mean. Or you're not. Are you accounting for like the censoring by age? Or are you also accounting for like the underlying variability and that there's some regression to the mean?
Yeah. So basically comes maybe a bit statistical, but so basically what we have here is like this Kaplan-Meier kind of curve. So like this cumulative incidence curve, and what you assume for this cumulative incidence is that there's like some certain baseline hazard, and that hazard is constant. But what you can put around that is like some kind of random distribution. So it becomes like a random effects distribution, and so you can say that the data is clustered within like families. Then, so we have maybe for every family you have like 10 or 11 people, and for all of those 10 or 11, you can imagine you can draw like separate lines for every family, and then you can estimate. So do those curves, are they still from like the same distribution, or are they really do they have a wider distribution? So can we assume like that the baseline risk of getting ALS is equal for every family, or is that different from every family? So it's in the technical terms, it's like a mixed effects Cox model that we fitted here.
But qualitatively, is the right way to think about it that if it looks like your family is on one of the extremes, the estimate would be a little bit closer to 25%.
Yeah, so it's being shrunk. Yeah, that's the
No, thanks.
Yeah, exactly. So
Oh, sorry, go ahead.
No, because this one should be like, if you count it like just on the family only, so then you would probably have around 95% or something, 90% for this family specific, because 5 out of 11, so that's 5 divided by 11 times 2, because we assume 2 of them are 50% is carrier. So that should be ending up around like 90-ish%. But you can see what the model does. So it shrinks that one. It says, well, that's very extreme compared to all of the other cases. So I shrink it down a bit. So the best is of course more data, more families. So that's
Another question that we did not get to yet, which is interesting. Did you create a model for one that does account for a rate of de novo mutations? And I think that would especially be families where there's literally only one case and there's no genetic info of anyone else.
No, so now we didn't know, but so Professor Veldink is also on this work. So he was of the opinion that the de novo risk of C9 is quite small. So that like the value of such a model, so developing only like a model for like de novo C9, if that even exists.
Just a small point to throw in there. Dr. Rademakers was on a webinar for us about TREM2 mutations a few months ago, and she casually mentioned, "Oh yeah, de novo C9." And I haven't run that down yet, but it seems like an interesting thing to think about and look into. And as I think I put an email to you, Professor, like even if we don't have the parents' DNA to test, even if a sibling of someone has the mutation, then you can be sure that it's inherited, because the odds of 2 siblings both having a rare mutation spontaneously is very low. So
exactly, so this is what that might be interesting, like for this family indeed. So is this a de novo or not? So the best way is to try. So can we rule that out in these kind of families? But but the best, of course, and that's some studies are going on now, is that instead of the questionnaire, we also ask all of the individuals, are you willing to provide DNA samples? So that we know, we can rule out whether that's like a true carrier or non-carrier, so that we don't need to make assumptions anymore. That would be the best study design, I think.
Just looking back through the chat here to make sure we got everything, every question. So, you know, I don't see, there is a question about the differences between repeats. Was that looked at in the people you had the DNA from versus their family history? Would have been interesting, I suppose.
Yeah, no, that's something that we're looking at now. So like so we have like for every family we have now like these individual risks. So we know like the high and the lower risk families, and so the next steps is indeed to look at like the repeat length of the C9orf72, but also at the maybe like some epigenetic factors. So we have a lot of data about these patients, and so maybe put in some new experiments to check, can we find like some kind of reason what's different with this C9orf case versus the other one. So those are very expensive experiments. So we're busy with that at the moment. Yeah.
There's a question about is it generally thought that sporadic cases are actually unrecognized familial cases? And Jennifer shared that sporadic C9 cases likely reflect incomplete penetrance. And I would just add that this paper, your paper, Professor, is like the first one to really talk about there might be a difference in families, but we'll let you also dive into it.
Yeah, so about the familial versus sporadic, yeah, I think there's like, yeah, I'm not officially like a geneticist, so my research focuses more on the other, more on the clinical trial aspects. But so the what I understand is that there's like that they want to let that go, the true classification between sporadic and familial, and that's very difficult to define what is familial ALS and what's sporadic ALS. So is familial only someone with another first degree or second degree family member with ALS, or could it also be like what you said before, like with FTD, for example, or like some other kind of I don't know, schizophrenia or some other neurological disease.
From a patient perspective, people who are healthy right now but are at risk, you know, ALS, FTD is one for us. It really is. Like, we don't want either, and
no, I can imagine
they are equally bad to us. So, from our perspective, that's something we would.
Yeah. All right.
I did have that one question. I don't know if you've thought about it at all, but you know, it seems if we're looking at does a penetrance, is that accurate for a specific family? It seems like a test could be, you know, what happened to their parent or their grandparent. You know, because a low probability event happening in succession, which I would say a parent-child is like rolling dice twice in a row or something like that, or a grandparent, you know, that's rolling a dice 3 times in a row. The same number, the same side popping up would be very low in a dice simulation. So I would think it would be pretty low in a 20% penetrance situation. So I would say if that occurred, you could just show right there that probably isn't accurate for that family. But did you have thoughts on that?
Yeah, no, I think that would be like a good, probably like the easiest test to make like a distinction between high or low risk families. But yeah, the other maybe a more feasible test would be if we can find like what makes why some C9orf72 gene seems to have like a different penetrance than the other one. So can we find something on that gene already? So then it could just be a simple biological, just like a biomarker test or something that we can just, we need, no, this is C9orf72 plus something else. So that's like a different risk factor than C9orf72 minus something. So yeah,
That's a very reasonable and a good thing for us to find. And I think the conclusions in the paper made so much sense, and we so appreciated them of, take into account family history when talking to people, get their family history, and that might impact what you say to them about what their chances are. And then also that, we really need probably some disease activity inclusion for any trials that are pre-symptomatic.
Yeah.
And that seems like even if it was 100% penetrant with the variable age of onset, that would probably be required also. So
yeah, exactly. Yeah. I think there's a lot of. I think this, for us at least, gave us a lot of information. Also, what kind of data do we need to collect? Because we have been collecting these kind of data for over 10 years, and then we end up with these kind of sample sizes. So, and we know also now the limitations about what actually we want to know. So we need to know from patients who carry C9orf whether their siblings are also carrier. That would be like the best to know, because then we can really try to start to estimate it. And not only the first degrees, but we also should expand to like third and second and third degrees. So there's a lot of renewed research ideas, I think, and like more information. We know much more which kind of data we exactly need now. So that's, for us, was a good learning exercise. This.
There's just a few minutes before the hour. Is there any last question from anyone or comments?
Oh, just going back to the de novo question, do you mind commenting a little bit about how that would qualitatively impact the penetrance estimate for non-de novo families?
Yeah. So suppose that, okay. So we consider that as being like, if we assume there's no de novo, that gives you like the most conservative estimate, so like the highest penetrance risk. Because, for example, if you have a parent and one of those got ALS, and we assume that there's like a possibility for de novo mutation, so it doesn't mean then that ALS at the parent level was caused by the C9orf. It could have been, I don't know, some kind of environmental factor maybe. So by assuming like some kind of de novo rate, you automatically in the end up always with like seems like a lower penetrance in our estimates. Not always I'm thinking of it, but it's it's a good way still to
and let me just provide a little context here, because this is a fantastic paper. Always just thinking about, are there any reasons why the true estimate would be higher or lower than what's reported? And so that's where the spirit of this question comes from, which is, when you think about all of the like uncertainties related to the paper, and you've accounted for a lot, it seems like one that could be relevant. I don't know if there's others. But I had thought qualitatively that if there were a decent amount of de novo, some of these families where there's just one case, if there was fallout from the penetrance estimate for the quote unquote familial, the penetrance rate might go up. But you're struggling with it. I was struggling with it. Maybe that's a ask for follow-up.
Yeah. No, I see what you mean. Yeah, I'm saying it. It can go either way indeed. So it can be that, you could exclude that, but you don't know which families to exclude in these data, because you don't know actually. So you would exclude then the families where there's no ALS observed. Very large families. But maybe that's more like a detailed discussion at one point. But it's an interesting take, I think. But overall, I think that the de novo rate, from what I understood, once again, I'm not a geneticist, but from what I understood, was very, very low for C9. So that's why we kept it simple. But you could play around, of course, with if there was more de novo cases, how would that affect the penetrance?
Maybe one follow-up, if it's possible, because it seems like the truth is probably that it is a relatively low rate. So if the truth were 5% or 10% of cases, you know, what would that do to the penetrance estimate? Is it negligible or not? I don't know if that's possible to estimate.
Yeah, I would find it difficult, because then you can no longer assume like that 50% of the cases are carrier. So you would have to randomly select like 10% of the families and say that's a de novo family, and then rerun the experiments and then simulate it a few times to get like the uncertainty around the penetrance. But I presume that then the average might still end up around like this 25%, somewhere in that range. But it's a good suggestion. Yeah, it's something interesting to look at.
Okay, thank you.
Yeah.
Well, wonderful. Thank you so much, Professor. I don't know if there's anything you'd like to close on.
No, not necessarily. Thank you very much for the nice questions and the nice ideas. I really enjoyed it. So yeah, thank you.
Thank you.
All right, everyone, have a great day, and we'll try to have the recording up pretty soon.
All right. Thank you.
Bye-bye.